Hello, everybody. Yeah, wait. Excuse me. We have midterm 1 on Monday. There is a homework also posted, but it is due only on Friday, so let me not bring that up now. There has been a cover sheet that has been of midterm 1 is posted. Try to access this wherever this is available. You should see the actual exam also at that place. So that should be an indication or should give you a feel for where to expect and what kind of exam to expect. It doesn't have any style questions yet, but still, since this is an online exam, it should give a feel for what is expected. That, as I said earlier, if you want to prepare for the exam, examples in homework plus lectures plus textbook examples, worked out examples. That's the 3 places to prepare for. Each chapter probably has about 5 plus 5 plus 5 or maybe 10 plus 10 plus 10 problems. So that should be a good a place or good collection of problems to look for. And I'll make sure that all my exam questions are based on this. It won't be exactly this, but very closely related to them. And that's it, I guess. I will be logged on Zoom during the exam, but that doesn't mean that you have to be logged on Zoom. It's up to you. You download the exam and upload it back. That is all that is needed. Oh, someone is saying, is he silent on my end? Do you guys hear me?
I hear you.
Yes.
Okay. Yeah. So thank you. So I will be logged on. If there is any questions, you can log into this classroom. Same thing. Zoom. I will be logged on. But you do not have to be logged on, but you can, if you want, you can log in like this and take the exam. That's also perfectly fine, but it's not necessary. Okay. That's it, I suppose. Any other things you think I should address here at this stage? Okay. Okay, so let me. Oh, I should also say all the topics we covered until Wednesday, that is what will be covered in the exam for midterm 1. Whatever we do today will go into midterm 2, or another way is that it will not be covered in midterm 1. Whatever I covered today should be sufficient for the next homework, just one lecture. There are only 3 questions in the homework. It's a short one. Basically, the homework 4 has been split into 3 because of the midterm that is coming up in between. And there is a third part which will be covered during Wednesday and Friday of next week. That will be centripetal acceleration. So today we want to talk about Galilean relativity. It is sufficient to say relativity, but we associate the word Galilean with it because more recently, in the last 100 years or 115 years, this was extended by Einstein, or it was corrected by Einstein, and whatever we do today is not exactly correct. This is an assumption that everything is moving slow. So if everything is moving slow in the sense relative to speed of light, then this works perfectly fine. But if you're within 10% of the speed of light, then there will be a significant error in what we do. Significant means about 10% error in the calculations that you get out of Galilean relativity. But we usually go significantly slower. Most of the time we are talking about, even if there is a spacecraft going, it is only about 10,000 10,000 meters per second, which is significantly about 10 raised to 4 times slower than speed of light. So even for a spacecraft, we do not have to take care of relativity into account. So what are we talking about here? It is relative measurement. So let's think of a ruler. So this is a ruler. It could be a main street of a town. And so this is a straight line. And let us say that is someone standing on the ground. Since the person is standing on the ground, we will call that the ground, G, right? So G stands for ground. There could be a car moving along the road. So let's say that's a car moving, and let's say that's car A. And let me not specify where it is moving. So that's the movement of the car, velocity of the car, if you want. Maybe I should mute all of you guys if it helps you guys. Okay, so that's car A, and there is car B going. And I don't specify the speed itself, but I will tell that in a minute. But what I'm interested in is what is the position of A with respect to the ground? Very straightforward. That's your position. And let me say this is R, position of A with respect to ground. So notice the notation here. So maybe I should clarify here. So this is R. This is R of A with respect to ground, means position of A with respect to ground, G, let's say A with respect. So that's the notation we are going to be using. What about B? There is a similar position, but this is also with respect to ground. So that's the position of B with respect to ground. And of course, you can also talk about what's the position of B with respect to A, right? That's a third quantity you can define here. And that will be this. So that's the position of B with respect to A. Right? That's the notation of. So the notation is of A with respect to G. Typically, we don't say that because we keep the origin fixed. Everything is with respect to the origin. But in principle, that is always with respect to possible. If that is the case, there is a clear geometry tells us what's the connection between the three, right? So position of R of B with respect to G is equal to, of course, this plus this, but let me write the opposite. There's a reason why I'm going to do that. So that's a position of B with respect to A plus position of A with respect to G. Notice when I say of B with respect to G, if I want to break it into two, I can introduce the A in that, and that can be used as a mnemonic as to how to remember the relative velocity if you want. But intuitively, it is very clear what is happening. This need not necessarily be in all happening along a straight line. You can very easily split this up in a plane or in a three-dimensional space. So this could be the position of B. Right? This is the position of B with respect to G. So let's say this is B, that's your G, and that could be your position A. That's position of A with respect to G, and you can have a position of B with respect to A. And that's also perfectly fine. That's a vector relation. We notice that, oh, position of B with respect to G is B of B with respect to A plus A with respect to G. That's good. So that's a vector relation relating positions measured by people with respect to some point. Oops, what am I doing? Let's see. Down. Yeah. Once we have the position, we can calculate the velocity, right? I just take the derivative of this. If I take derivative, this is g with respect to dt is equal to a with respect to t plus t. And that immediately tells me this is my velocity. Velocity of B with respect to ground is equal to velocity of B with respect to A plus velocity of A with respect to G. I mentioned earlier, I made a comment that we are doing Galilean relativity, and this is different from what is known as Einsteinian relativity. And what's the difference is that when we take the derivative here, we have assumed that the time is the same for all three persons. Here there are three persons involved are A, B, and G. And when we take the derivative, we didn't care for whether the time is the same or not. And that's the slight difference between Einsteinian relativity and Galilean relativity. And that small change leads to what is called, the results are entirely different. But the difference is only relevant if you're going at almost at the speed of light. We won't discuss that. For us, this is the equation. If there is three velocities, that's how it will be related. We come across this all the time. If you were going on an interstate along the straight line, this comes out very straightforward. If there is a car A going with, let's say, 70 miles per hour, right, and car B is, let's say, going in a lane next to you, and that's going at 80 miles per hour, then it doesn't seem like if it is in the same direction, if you're sitting in car A, it seems like B is going very slow, right? It will be actually 80 minus 70. So velocity of B with respect to A, velocity of B with respect to A is 80 in the I hat direction minus 70 in the I hat direction, right? Both are in the same direction, so that's 10 times I hat. Very straightforward. Right? If it was going in the opposite direction, in fact, it will be added up, so minus of a minus. So another example could be that here, A is 70 miles per hour, and B is actually going in the opposite direction at 80 miles per hour. You will do the same example again now, so it will be velocity of B with respect to A would be 80, minus 80 in the I direction, minus 70 in the I direction, and they add up, and that's minus 150, significantly larger, which is intuitively very clear when you, if you have experienced how things move on an interstate. It is much more dramatic when it is actually A is equal to B and you're not on an interstate. If you're in a subway car, in the trains, this is very common because you don't have a reference to look at outside. If it's an underground train and the only thing you see is through the windows and into the another car, especially when you when it is going with uniform velocity and both the trains are going at the same speed, 70 miles per hour and 70 miles per hour, it might be hard for you to realize that actually you're moving. And that is a true statement, that if you do not have any reference to look outside, like that means to say you cannot have stars as a reference, then there is no way you can detect that you're actually moving. For example, we are moving at a tremendous speed of about 10,000 meters per second. The Earth as a whole is moving in around the sun at that speed. But if not for the stars that you can use as reference, there is no way you can conclude that you're actually moving, which is pretty remarkable that that should be the case. And that is an idea of inertial frame, which we will sort of emphasize in the next chapter again. So having mentioned that, let's do slightly more involved problems. This is all one-dimensional, slightly comes out very clearly, but now let's do this in 2 dimensions where things are going not really in along the same line, but in different directions in a plane. So let's do an example now. And the example is about a boat going or crossing a river. So there is a river. These are the 2 banks of a river, a bank 1, bank 2, and there is a river flowing. So this is a river. And the water is going, moving steadily in the river, and let's say the speed with which it is moving is about 5 meters per second. That's 5 meters per second. And that will be the velocity of the river with respect to the ground. We are going to talk about 3 different velocities. So I point out that this is velocity of the river with respect to the ground. I should have a direction because it's a vector. So I put in an I hat. So R stands for river, G stands for ground. And we are going to have a boat cross this river. So let's have B for that. So this is the velocity of the river, and that's horizontally moving to the right side. So we have a boat, and if we are driving, or if you're driving the boat for the first time, we may not have this experience of how much you're going to get drifted. And naively, you would, if you want to start from here and reach the other side across the river, you might actually try to aim right in the opposite direction. And this is what you might do, right? That's your velocity of the boat. But what do we mean by velocity of the boat? This is the velocity of the boat with respect to the river. What does that? So this is velocity of the boat with respect to the river, in the sense that when you're actually controlling the odometer or the steering wheel, you're in the river, so it is with respect to the river. Odometer touches the water, and that is how it controls that. Or if you think of a car, how do you control the steering of it? In what direction you want to go? It is with respect to the ground. Similarly here, it is all with respect to the river. So whatever is happening here, this velocity, you're trying to go there, but you're not going to end up there because a river is going to drift you off. You're going to be off from where you want to go. If you start from here and you naively aimed at that, but you're going to get drifted. And we want to talk about what is the, how much do you get drifted off. So we come back to our velocity addition relation. So we would like to know what is the velocity of the boat with respect to the ground. If you are standing on the ground, you will realize that the boat is not really going vertically up across to the other point. Instead, it is getting drifted. So the velocity of the boat with respect to the ground is equal to the velocity of the boat with respect to the river, right? Velocity of the boat with respect to the river plus the velocity of the river with respect to the ground. That's our velocity addition formula that you can introduce a third quantity and then you can have a addition formula in there. In the vector relation, you see that velocity of the boat with respect to the river is a vertical vector. Velocity of the river with respect to ground is a horizontal vector. And using vector addition, we know that, so if this was the relation, so this will be your velocity of the boat with respect to ground. And intuitively, we realize that yes, if the river was going to drift the boat, you will end up moving in that direction. So instead of going from here, you might reach somewhere there. So what is the velocity of the boat with respect to the ground? Just put the addition formula here, right? So since both the velocity are purely either in the X or Y direction, it is straightforward. In fact, you can actually do it using the triangle itself, right? This is already in the form of a right triangle. So it is slightly easier. So velocity of the boat with respect to river, so that's 5.0, sorry, this is the opposite, right? So this is, oh, I should give you some numbers here. So that's 15 times J. So the boat itself is moving at 15 meters per second, which is about 30 miles per hour. So that's 15J hat plus 5.0. And the vector is shown in the diagram. Notice I should, let me switch it so that there is no confusion. So that's 5.0 I hat plus 15 J hat. Typically we write the X in this direction. What is the direction it makes with the vertical? If I put that as the angle theta with respect to the vertical, tangent theta is clearly 15, no, right? Tangent theta here is the X component over the Y component. Notice the angle here is not the usual one. Usually you would have given this angle. So that's 5 divided by 15, and your angle theta would be 1 over 3, tan inverse of 1 over 3. And that's about 18.4, but since I gave 2 sig digits there, so that's 18 degrees. That's your angle theta. What is the speed with which actually the boat goes? It will be faster because it has a drift from the river also, so it's going to add up to that. So, well, what is the speed with which it goes in? So let me erase this so that I have some space. So the magnitude of the boat with respect to the ground will be equal to 5 square plus 15 square, and that's equal to 225. Why is this not working? Oh. Again, 15 square plus 5 square. I think I was trying to be quicker. So this is 16 meters per second. Again, reasonably intuitive. You're trying to go there, but instead you get drifted. There is one more thing you can immediately do. If it is really going to get drifted, you can ask how far are you going to get drifted, and for that you will need some more information. Let's say that this is 200 meters. And we could ask, how much does it get drifted in the horizontal direction, x? Since it is going with uniform velocity, this angle that it forms between vectors related to velocity will be the same as it forms for displacement also. So you can immediately construct a triangle. This is x, that's your 200 meters, and it will be the same angle theta, which is 18 degrees for us, with the error that it was actually 18.4, but to 2 sig digits, you round it off to 18. So you can calculate x to be equal to 200 times tangent of 18. And that gives us 65 meters. That's good. We can actually add a small discussion to this. One might wonder, what if you were not naive and you actually tried to be careful about this drift, and you instead moved in the opposite direction, right? Typically what you do is, if you want to not get drifted, instead you want to reach right at that place, you will actually aim your boat to the left at an angle. And then the question comes, at what angle should you aim for, so that you actually reach right across that point? And it is not exactly angle theta, it is slightly off from that. It is close to that angle theta, but it is not exactly the same. So let's see how much should be the angle and how different is it. So notice again, so suppose I would draw this here, or yeah, let me erase this part. So now I have a new figure. So that's your boat, sorry, that's your river, and you still have the velocity of the river with respect to the ground. That's identical. But now we do not want to go vertically up. Instead, you're going to go at an angle, so that you will end up going vertically straight. Right? So we learned from the first time, we realized we were not careful, so we got drifted. This time we will get drifted, but we'll accommodate for the drift by going at an angle theta prime, let's say. So this is theta prime. And what should theta prime be? And our condition would be that we are going to go at the same speed in this direction. So this is still going to be 15. So the boat can go at 15 meters per second. So we'll keep that fixed. So this is 15 meters per second, and that's 5 meters per second. And so what is angle theta prime? Right from this triangle itself, you can see, or you can write the vector equation and get the quantity out. And this time you notice that it is not tangent theta, it is actually sine of theta prime. That is 5 over 15. So this is 5.0, 5 over 15, which leads to angle theta prime will come out to be very close to the earlier, because for small angles, sine theta and tangent theta are very similar, but slightly off. And if it was a bigger angle, then it would be significantly off too. The remote, I need the calculator. So that's 5 divided by 15. And that comes out about 19.5, so that's about 20 degrees. So earlier it was 18 plus or minus 1, right? So it was 18.4, so that's about 19 degrees, and this is about 19.5. So it's very close to each other, and maybe if the error is large, you may not even be able to differentiate between them, but very roughly speaking, that's 18 degrees, and that's 20 degrees. What's the resultant speed? That will also be different. Here, this will be smaller than 15, right? 15 has to be 5 plus this. So what is the velocity of the boat with respect to ground this time? So this will be equal to whatever is the speed here, using the right angle formula, should add up to 15. So this is 15 square minus 5.0. And that's equal to, it's 225 minus 25, that's 200 square root of 200. So that's about 14 meters per second. Again, very close within the error bar, but different, right? And these are the problems where the methodology, if there are points being given for methodology, then even if the numbers are the same, if you're not used sine or tangent in the right way, that's relevant if you're being assessed for that. So let me do another example. Any questions on this part? Should be intuitive enough. Okay, so another example which you come across on a I would say on a reasonably common, it's common knowledge, we can say, is rainfall. Correct? And there's also an example related to this in the homework. Let us say rain is falling down, vertically down. So if there is a wind and other factors coming into this, then you actually get proper vectors coming in. And I will try to do that example. One of the examples related to airplane and a wind, that's a good one. But let's do a simpler example here. And typically, what is the speed with which raindrops fall? It turns out that it's about between 5 to 10 meters per second. 10 is really large. So let's say it's about 8 meters per second. So that's 8 meters per second. So that's the speed with which the rain is falling, and it is falling vertically down. You are actually driving on an interstate, and let's say you're going significantly fast. And if you're inside a city, you will be going at 40 miles per hour. If you're on an interstate, you will be going at 32. If it is 70 miles per hour, it could be 32. So let's go all the way fast. So this is 32 meters per second. So it's about 4 times. So this is not really the scale. So that's your, that's a vector representing your, you are in a car that is going at that level. So there are 3 quantities now. Rain, R is for rain. Right? There is ground still, there is ground. And let's say now this time we have a car. So this is car. Same idea as earlier, but I want to point out what will be the difference between rain or snow. So, or what will be the difference in that case. So how does it work? This is the velocity of the car with respect to ground. And this is the velocity of the rain with respect to ground. One is falling vertically down, one is going horizontally with respect to ground. But if you're inside the car, you will observe the rain with respect to the car. So we would like to know what is the velocity of rain with respect to you, which is you're in the car. So what is this equal to? That's what you would like to calculate. So velocity of rain with respect to car is equal to velocity of rain with respect to ground plus velocity of ground with respect to car. Right? That's a simple way of introducing this, that rain with respect to car is rain with respect to ground, and ground with respect to car. Right? That's how we introduce the relative velocity. If you want, this is inserted in here if you want. But that's not what we have. We have velocity of car with respect to ground, not velocity of ground with respect to car. But velocity of car with respect to ground will be exactly opposite to the velocity of ground with respect to car. So that's an observation, or in general, velocity of A with respect to B is minus of velocity of B with respect to A. So that's gives us, this is velocity of rain with respect to ground minus of velocity of car with respect to the ground. And that tells us what we have to go. We have to flip it, right? So velocity of car with respect to ground, we have to flip it. So this is your rain with respect to ground. If I flip this, this turns over in the opposite direction. And then we see that, oh, velocity of the rain with respect to car is tail to head. And that is exactly how we observe the rain, right? It is coming towards you. Here you would have thought, oh, how do you add up? It is actually going in the bottom direction, but this is how the addition works. So this is velocity of the rain with respect to ground. And this is minus of velocity of car with respect to ground. Right? Or this is the best way to put it is G with respect to C, which is C negative of. And then we can calculate the angle clearly. Yeah, I won't calculate the velocity of the rain with respect to ground, but we can calculate the angle, which is what we see usually. And tangent theta, theta would be equal to tan inverse of 8. This was 8 here, and this was 32. 8 over 32, and that's equal to tan inverse of 1 over 4. And that's about 14 degrees. So let me write that here. That's 14 degrees. And you will notice that as you go faster and faster, this number.
Shouldn't it be 8 over negative 32?
Oh, did I make a mistake? Tell that again. Could you repeat, please? I cannot hear. You're muted, Blake, if it is you who is speaking.
I think he asked if 32 should be negative.
Oh, no, because I switched that, remember. Like I switched the negative already, and now when we are adding the vectors, this is down and this way. So no negative, and even otherwise, remember, whenever we are doing vector addition, we are looking at the angle as if these are all magnitudes of the numbers. So that when you're looking at this angle, it's a right triangle formula. Distance of this divided by this distance of this. No, don't double count on this negative signs. So that's the way to say it. So hopefully I answered Blake. I think I'm not able to hear you. I see he cannot hear me. So one of you guys help him. Sorry. Okay. So that's 14 degrees. Good part here is that as you go faster and faster, this 14 is going to get smaller and smaller. Right? This is going to get stretched out, and this angle is going to get smaller. In fact, you go slower, this angle keeps increasing, and that's what sometimes you think of as whenever you're moving. The moment you get into the car, it seems like it is raining heavy, and when you stop, the rain has stopped. So that's an illusion in the sense that you're since the angle is changing, there is more water that can come and hit your windscreen. So it's an effect of that sort. It is not that actually whenever you're driving, it starts raining more. There is one more point you can make. Of course, here the control is on the speed. We can also talk about snow. Now, snow is very significantly different from rain in the sense that they are much more lighter, so they don't fall so fast. So they fall significantly slower. So what's the change there? And the change there is that snow falls very slowly. So it's usually 1.0 meters per second. Rain, typically the speed is about 5 to 10 meters per second, depends on the size of the raindrops. The terminal speed of a raindrop is decided by how big it is. Snow also gets decided by how big the snowflake is, but it is significantly lighter, so that terminal speed is only about 1 meters per second. And if you're going at 32 again, so you can again ask what is angle theta. Let's keep it the same, so that's 32, and you would calculate your angle theta to be tan inverse of 1.0 over 32. You can already see that's a significantly smaller number. So even diagrammatically, you can see that that will be significantly smaller, but just to get the number, so that's 1 divided by 32, and that's about 1.8 degrees, right? Which is almost horizontal. And you might have observed that whenever snow is falling, snow seems to be coming towards you while driving exactly horizontally, like it seems like there is a point from where all the snow is. So it's a nice effect to see using these equations. Those are examples where I have provided most of the numbers along the x or in the y direction. That's a slight simplification. Not every problem involves that. Sometimes you have to have more complicated expressions, and let's do an example there. And but if you're a pilot and you're controlling the aeroplane, that's what you have to do. And let's see, construct a problem like that. And this is also closely related to what you have to do in your homework. So let's say, again, example. So this could be your north-south direction. That's your east, that's your north. And let's say, like in the boat problem, let's say you have to reach, you want to reach somewhere in the north direction, like with respect to Carbondale. Let's say you are in Carbondale and you are piloting an aeroplane and you have to reach Chicago, which is pretty much closely to the north, right? So you want to reach here, you start from there. That's your velocity of this time aeroplane, A for aeroplane. And let's say G is ground again. And this time we have a wind, right? So this is the wind, not to be confused with west, right? West also has W in it, but we're not talking about directions, doesn't come underneath this W. So velocity of the aeroplane with respect to the ground, this is what we would like to have. Right? So like in the boat, we would like this to be the case. Resultant should be here, but there is a wind now, right? So you have a wind that's blowing, and this is the velocity of the wind with respect to ground, and it need not be in the north or the west or a particular nice direction. So it could be making an angle 30 degrees with north of west. That's what I have provided in your homework. So velocity of the wind with respect to ground, this could be having a magnitude and direction given to us. So let's say this is equal to 30 meters per second, and at 30 degrees north of west. So that's that quantity in here. So that means velocity of the wind with respect to ground would be 30 times cosine of 30 degrees. So that's 30 speed, and this is an angle, and this is negative plus, so that's I hat direction plus 30 times sine of 30 in the j hat direction. That's your velocity of the wind with respect to the ground. And let's say the velocity you would like to have in the north direction. So if you know at what speed you have to, in how much time you have to reach the destination, you would know exactly what is the speed you would like to have. In general, this could be in some other direction too, but since it is not, so this is 0I plus, let's say this is given to us to be, let's say 75 meters per second in the j direction. So that's 75 in the j direction. Again, suppressing the units there. And the question could be that how do I, in what direction would you try to actually take the aeroplane in so that you reach there? So wind is in this direction, so you know that you will have to actually move in the northeast direction so that after the drift you reach it there. So you would like to go in this direction, but at what angle? That's the question. So you would say, what is the velocity of the aeroplane with respect to the wind? That's what you're interested in. Because what direction you head towards, that is always with respect to the wind, because what is the aeroplane in touch with? That's the wind. That is what controls the effect. In that sense, it is the velocity of the aeroplane with respect to wind that is being in control. What is that equal to? Velocity of the aeroplane with respect to ground plus the velocity of the ground with respect to the wind. But we flip this immediately. This is equal to minus of that. So this is minus of the wind with respect to ground. So if it was plus, this is g of w, but velocity of a with respect to b is negative of velocity of b with respect to a. This immediately lets us calculate this. I have to subtract this minus that. So this is 0 minus of minus. So that's minus of minus 30 cosine 30. That's I hat. And again, I have to do 75 minus. So this is 75 minus 30 sine 30 is actually 15. So that's 30 sine 30 in the j hat direction. That gives us a positive quantity here, and this will be 15 minus 75. So both are positive quantity. That means it's in the first quadrant, and that's what we expected. Like we should take it in a particular direction. So let's calculate that direction. First of all, what is the number? 30 times cosine 30. So that's 26 I plus 75 minus 15. So it's 60 j hat. So the magnitude, or first let me get the direction. Direction would be tan inverse of, let me draw a diagram here. So that's velocity of a with respect to g. Sorry, velocity of aeroplane with respect, did I say that correct? No, velocity of, I would like to see velocity of aeroplane with respect to wind. And that's your angle you can calculate. So that will be equal to 60 divided by 26. So that's 67 degrees. What's the speed with which the aeroplane will go with respect to the wind, not actually with respect to the ground? So velocity of aeroplane with respect to the wind, magnitude wise, would be 26 square. Squeeze that in here. Hopefully not confusing. Plus 60 square. Visible? Yeah, not bad. That's equal to That's 65 meters per second. Right, you're going at 65 meters per second, significantly slower, but the wind is going to drift you. The wind is 30 meters per second. Wind is typically not 30, like a small wind would be about 10 to 15 meters per second. So 30 is on the higher and it's almost like a strong wind. So that gives you an idea of what if the vectors were not exactly in the X or Y direction. And let me stop right. I think I'm pretty much on time for a change. Thank you, and good luck with the exams.
I have a question, please.
Yes, please.
Actually, I have a question about homework for. I submit mine. I try to submit mine, but I cannot because of my internet. I have a very, 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 very weak internet, and I am not in Carbondale. I am in my home. I tried a lot to submit it, but I can't. And I tried to send email for you, but also I can't because my internet. And now when I fix my internet, I send it to you by the email. So can you accept mine?
And can you send me an email on that, and I'll respond to that by email as I have been doing to everyone?
Yeah, I sent it to you by the email.
Sure. And one thing is that there is usually I don't accept late homeworks. That's one thing. But
no, I submitted on the time, but
yeah, then
they
it's okay if you submitted it on time.
Now my homework it's not submit, but when I tried to submit it, they said I can't because I have to add a file or something like that. When I submitted, they took long time. My internet it's weak, so I cannot
understand.
submit mine.
Yeah, so send an
because
email,
of my
but
internet.
here is a
I
point.
swear that I try to submit it on the time, but it's take more time with me. That's why. And when I try to send it to you also on the email, but it's also took more time with my internet. So I send it.
I hear you, but the point I have to make is that I will make the judgment after reading your email. But the point I wanted to make is that whenever these kind of things happen, I intend to drop one homework for everyone, right? So hopefully that will take care of this. But if this happens more often, then you have to be more careful and submit it on time.
Yeah, I know. I will be very
so if this is the only time, you should be okay. But send me an email.
This is it. Actually, this is the first time it's happening to me, and I tried a lot to fix my internet, but I am in my home, and my internet in my home it's very weak. That's why. So I promise it will not happen again. Thank you so much. I appreciate that. Thank you so much. Bye.
Any other questions? Seems like Blake, you had trouble, huh? Yes, someone. Yes, please.
For the midterm, we print out the cover sheet and then we scan that filled out with everything else, right?
Yes. Oh, that's a good question. You don't, as far as the honor pledge goes, you can rewrite that, rewrite the pledge on your paper sheet. That's good enough. You don't have to really print the cover sheet. The pledge is all that I need from there and your worked out solution on your notebook. So the cover sheet itself is not significant, if that helps you. Did I answer your question?
Yes, thank you.
Good. Yeah, Blake, you also mentioned that, so maybe I will clarify that in an email or something. Yeah, but it's okay if people can submit the cover sheet. Why not? Yeah, sure. I think that should be fine. But again, the full answer on a homework version of these questions would be the velocity and the angle. Yes, that's correct. I did calculate the velocity also, right? Yeah, velocity and the angle, yes. Yeah, thank you. Yeah, okay, good. Okay. Sorry, you had trouble. You're the one who corrects my numbers. Good. Shall I stop here?
I just have a last quick question. Like
Sure.
on the Monday, like after we get the question paper, like what
Mhm.
time we should just submit it on the D2L with the answers?
The submission will be open from 12 o'clock to 12:50, anytime during that time.
And we don't need to like it's not mandatory to be on a Zoom meeting, right?
It's not mandatory. I
Or-
need the submission,
Okay.
and yeah, that's all.
All right. Thank you, sir.
Mhm.
Hmm.
Blake, you still cannot hear me, I suppose. Okay.
Okay, what
think
is going on here?
I'm going to stop. Or do you want to figure out, Blake? I think I should just stop here, I guess.